Hello, I am Václav Novotný and welcome to the tutorials of energy sources and conversions. In this short tutorial, we will have a look at the stack loss, a simplified way how to estimate boiler efficiency, and we will talk a little bit about ideal gas. Okay, so let's get to our problem. The problem goes that we have to estimate stack loss, or also we could call it loss by flue gas sensible heat, and boiler efficiency for wood combustion by a simplified method. What do we know are following things. The lower heating value of the wood, which we are combusting, is 15 megajoules per kilogram. We are provided with the amount of required air for ideal combustion of this wood, which is 4.05 normal cubic meter of air per 1 kilogram of wood. We know the ambient temperature, and we will calculate the results for two cases of flue gas temperature exiting from the boiler, being 150 and 200 degrees C, and for three cases of air excess, being 1 for ideal stoichiometric combustion, 1.5 and 2. The simplifications we are talking about are following. We are provided with the amount of air for ideal combustion. Otherwise, you would need to know the composition of the wood and perform stoichiometric calculations, to which we will probably get in some other tutorial. Also, the flue gas properties will be substituted by ideal gas, and not just ideal gas but even perfect gas. The ideal gas is a model that follows the ideal gas equation. The perfect gas follows all the rules of ideal gas, but on top of that they have the constant specific heat capacity, which is in our case 1.005 kilojoules per kilogram and Kelvin. Ideal gas in general doesn't need to have this specific heat capacity constant. And the last simplification for the boiler efficiency, there will be no other losses than the stack loss. Just briefly talking about the stoichiometry, that would require solving the chemical equation, like here, if we would have the concentration of carbon, hydrogen, sulfur, or eventually other components, and we would be searching for the required amount of oxygen for that to get the combustion products. Then the air excess is the ratio of actual air for going into the combustion chamber compared to this ideal amount. Now let's talk a bit about the ideal gas equation. The way we will need it in our problem is to convert the normal cubic meters into the kilograms, because also, for example, the specific heat capacity we have is in kilograms per kilojoule and kilo. So you probably know the ideal gas equation, that in the form that goes as follow. PV is nRT, where P standing for pressure, V volume, N number of moles, R ideal gas constant, and T being the temperature. Now we can rewrite it in the following way, that the V, the absolute volume, is unit volume. Just so that you know, we will be using capital for absolute values, capital letters for absolute values, and lowercase for unit or specific values. For example, here in the V it would be volume, but same can go, for example, for enthalpy, entropy, and so on. So PVM, V times M being the capital V, is nRT, and from this we can get to PV equals N over M RT. And now this N over M is actually 1 over capital M as molar mass, because molar mass M equals m over n. So we can actually write PV equals R over m multiplied by T, and this R over m is also very often referred to as lowercase r, which is specific gas constant. This just because the m, the molar mass, is different for different gases, so this is specific for each different gas that we are using. Now for the air, the molar mass that we let's put it here, m air. The molar mass of the air is approximately 29 grams per mole, meaning also, or being also 0.029 kilograms per mole. Now I will put it in here. The R, the universal gas constant, is 8.314 joules per Kelvin and mole. So combining these together, we get that the R equals capital R over M, which is 8.314 divided by 0.029, which is 287. And now let's have a look at the units. So the R is joules per Kelvin and mole, and the M is kilogram per mole, so it's mole and kilogram, and see the moles cancel out, and the specific gas constant is then in units 287 joules per Kelvin and kilogram. Okay, so now we have this equation PV equals RT, and for the normal cubic meters, so what does the normal mean? The normal means that the temperature is 0 degrees C and pressure is 101.325 kilopascals or 101,325 pascals. So now we know the temperature, we know the pressure, we have the specific gas constant, and we can get the V as specific volume. So specific volume equals RT over P, and one more thing we can write. What is the specific volume? Specific volume is just inverse value of density. So now we can make the calculation. Just please don't forget that the temperature needs to be insert it in degrees Kelvin. So the V equals 287 times 273.15, the temperature of 0 degrees Celsius in Kelvin, divided by 1.1325 pascals, and the result should be 0.774 kilogram per cubic meter. Okay. Or the density goes that the density is 1.2925 kilogram per cubic meter. Okay, so now we have density of the air, which is in simplification also for, in our case, the density of the flue gas, and we can get the mass flow rate of the combustion air. So M of the combustion air would be the required volume of the combustion air multiplied by this normal air density, with normal because it's defined with respect to the normal conditions. So it's 4.05 normal cubic meter per kilogram of the fuel, multiplied by this 1.2925 kilogram per cubic meter, or actually also normal cubic meter, because it's defined at the normal conditions. So putting that together, we get the result being 5.2 kilograms of air per kilogram of fuel. So this is the combustion air, but we want the entire amount of the flue gas. So the M of the flue gas, now at first for the excess air, which we mark alpha, excess air equals 1, is this mass of the combustion air, plus also this, the combustion air is a kilogram of air per kilogram of fuel, and also we need the part of the fuel that goes into the flue gas. In our case, we will make another simplification that we say that all the fuel is turned into the flue gas, and that means just that we neglect any ash, which in case of like wood combustion, it anyway has very small ash content, like 1 to 3%. So the mass of the entire flue gas for the ideal combustion is mass of the combustion air plus 1. And yeah, units. Now it's here was kilogram of air per kilogram of fuel, and here it would be kilogram of the flue gas per kilogram of fuel. So we have the mass flow rate, and how do we get the amount of heat that is contained within this flue gas stream? The heat, or what we use, is the calorimetric equation. So Q as heat equals some mass multiplied by some specific heat capacity multiplied by difference in temperature, so delta T. Now, in our specific case, where Q of the flue gas when alpha equals 1 is the mass flow rate of the flue gas at alpha equals 1 multiplied by the Cp and multiplied by the difference between the flue gas temperature minus the ambient temperature. Then when we will evaluate the boiler efficiency, so we should use as the ambient temperature also the reference temperature to which the lower heating value is defined, but in our case both are the same as 20 degrees. 20 degrees was defined here as the ambient temperature, and 20 degrees is the standardized temperature for evaluation of lower heating value. So now let's put there the numbers. So the flue gas, it was combustion air plus 1, so it would be, let's have it also here for completeness, 6.2347 kilogram of flue gas per kilogram of fuel. Multiplied by 1.005 kilojoules per kilogram Kelvin, and multiplied by the temperature difference. In the first case we will take the 200 degrees C minus 20 degrees C as ambient. So when we put it together, we should get that the amount of heat required is 1128 kilojoules per kilogram of fuel. Yeah, this we have kilogram of fuel, flue gas per kilogram of fuel, and this heat capacity is also with respect to kilogram of the flue gas, of course. So this is the amount of heat for the alpha equals 1, and now what happens if the excess of the air is higher? So in that case it would be that additional air is not taking part in any combustion, it's just there. It's sometimes necessary to make sure that all the fuel is burned so that each molecule of fuel can find its molecule of the oxygen, but in overall balance, this additional air is just a ballast which does not take part in the reaction. So we will call it Q ballast. And it will be now 1 minus alpha, because we already calculated that part of the heat. This is expression of the extra air, and multiplied now by the amount of combustion air per kilogram of fuel. In here. And again multiplied by the specific heat capacity and temperature difference. So this member is the mass of the ballast air from the excess, from the air excess. There is not the fuel anymore. This is just the extra air, and multiplied by Cp delta T. And now for the case the overall heat of the flue gas at any air excess then can be written as amount of heat, the heat at alpha equals 1 plus the ballast heat. Now let's have a look how it will look like with the efficiency. So let's have a look at this figure where we have the system of the boiler, and there are 3 streams of the heat. There is heat going into the boiler as in the form of the fuel, and then there is the useful heat, and then there are the losses, where here we assume there is just one, which is the stack loss. And this is also the general thermal and energy balance which we will use in basically most of the calculations throughout the energy engineering. So because it's steady state, the energy cannot there is no accumulation of energy, and also the energy cannot disappear, it can just change its forms. So the input of the fuel will have to be the sum of the output. The input of the heat needs to be the sum of the outputs. So how it will look with the efficiency. The efficiency is always a ratio where we have some now with respect to heat, so useful heat, the heat that we get out of the system for some or energy which we get out of the system for some use, divided by overall energy input. Now in our case, what is the useful heat? We did not calculate it directly, but we calculated the heat in the flue gas which is lost. This, or the as we call it, the stack loss. And from the balance, it needs to be the heat input in the fuel, or also denoted as Qn or LHV as lower heating value, minus the loss, so this is the useful part, divided by the input, which is the Qn. So now let's put here numbers for our first case with excess of the oxygen being 1, so ideal combustion. So it would be the lower heating value being 15 megajoule per kilogram of the fuel, minus the Q stack, or generally all the losses, which we will need to also calculate in megajoules per kilogram of the fuel, and the heat input, you already have it here, like this. Yeah, now just this for alpha equal 1, so the loss is 1.128 megajoules per kilogram of fuel. So putting that again, calculating the numbers, we should get that the efficiency should be 0.9248 or roughly 92.5%. So already in case of ideal combustion and 200 degrees C outlet temperature of the flue gas, we get it eats 7.5% of the efficiency of a simple boiler. And here, as the last thing, we can see the values for the range of parameters which were specified in the problem, where, for example, for the boiler efficiency, we can see that with the low temperature of the flue gas outlet and ideal combustion with excess of the combustion air being 1, being quite decent at around 95%, while if we increase the excess of the air, the efficiency decreases. If we increase the temperature of the flue gas outlet, so of course also more heat goes wasted, efficiency decreases, and in our case down to 86%. So that's it from today's tutorial. See you in the next one.